A lovely set of integrals here. They look pretty complicated, but using substitution, we're going to make it all work out. So first up, part one, we're asked to use, we're given a lot of guidance here to use this substitution, and the other integrals are going to be along similar lines to find this integral. So let's find du by dx. Okay, first up the product rule. So I'm just going to get sine x when I differentiate x and keep sine x the same, and then it'll be x and differentiate sine x, and then differentiate cos x to give minus sine x. These two cancel. So dx by du is going to be 1 over x cos x. And therefore the integral let me call this I1. So I1 is going to equal, now let's get the substitution in so I can replace dx by du, and this here is 1 over x cos x. So what's going to happen is that the x's are going to cancel here, and then I'm going to be left with the integral, and I'm going to times the denominator through by cos x. So tan x is sine x over cos x, times through by cos x gives me x sine x plus cos x. Now, where have I seen that before? That's right, we simply have the integral of 1 over u with respect to u, which is going to be ln u, don't forget your plus c, and hence ln, substitute in u, it's going to be x sine x plus cos x plus c. Nice. Still in part one, but let's look at the next integral, and I'll call this I2. Okay, so we've got to make our own substitution up this time. Note the tan has changed to a cot, so it kind of seems to make sense that we're going to have to swap around the x sine x, because remember when we differentiated that, we ended up with a sine x, and it cancelled out with something, and we ended up also with x cos x, and then dividing by that cancelled out the cos x and the tan. So this kind of makes me think we should go not with x sine x, but with x cos x, because when we differentiate that, we'll be left with a minus x sine x, and the sine x might cancel. Let's just go with it. There's also a minus 1 here. So instead of putting plus sine x, I'm going to put minus sine x. Remember, we can always modify the substitution if it doesn't quite work out. It's actually going to. I had doubts about it along the way when I did it first, but it's going to all check out. So du by dx is going to be cos x, then minus x sine x minus cos x. So I2 is the integral x over x. I'll leave it as cot x minus 1. Now I'm timesing by dx by du. That's going to be minus 1 over x sine x. Du, the x's cancel, and I'll get the minus outside the whole integral. You could do that, just put it outside, absolutely fine. Times x cot x by sine. Cot x is cos over sine, so we're just going to get x cos x minus sine x. And again, we've got u on the bottom. It's just this time it's minus 1 over u du. That's okay. We're just going to get minus ln u. I'm even just going to substitute it back in straight away. Okay, we are on a roll. So Part 2, use the substitution to find this. Let's call it I3, funnily enough. I know I didn't quote it in the last one, but just in case we need to. Okay, well, we've been using a slightly different thing to the denominator, but if you think about what there is a relationship between tan and sec. Noticeably that if we differentiate tan x, then actually we get sec squared x. So maybe we can cancel it out. If we let u equal, why not we just go with x sec squared x minus tan x? Because when we differentiate this, we're going to get a sec squared x. And another term, we differentiate this, we're going to get minus x squared x, so it can cancel out. That's what we're trying to do along similar lines. Seems a good starting point anyway, given no other suggestion. And it is going to work out. So du by dx is going to be sec squared x. And then I'm going to need to differentiate sec squared x, which gives me, okay, just use a chain rule here. So bring the power down, reduce the power, times by the derivative of sec x, which is actually sec x tan x. Such a great derivative, it actually involves itself times by tan x. So we get 2 sec squared x tan x. So over here I'm going to get 2x sec squared x tan x. Now I've got to minus derivative of tan x, which is sec squared x. And these cancel. So dx by du is going to be 1 over 2x sec squared x tan x. Okay, so I3 is going to then equal the integral right this time, because it's not going to cancel out in any way, it's just u here directly, and then times in by 1 over 2 x. It's just all going to cancel out. Du. That cancels with that. I've just got that. I've just got a half. Don't forget about that. So we've got a half integral 1 over u respect to u, which is going to be a half ln u, or should I say ln x sec squared x minus tan x plus c. Hey, save the best for last, this one here. Now we're on a roll with getting through these quickly. This is going to be no problem, right? Um, well, I did first of all make a wrong substitution. I started just thinking, okay, can I write this as double angle formulae and somehow combine them? But didn't really seem to help. The x is a little bit strange because we've not dealt with an integral yet with an x there. So after I'd tried a couple of things, thought about it, I thought, okay, what if we try to get rid of that? Let's just bear in mind when we're doing this question, we have this one of like an I view. Okay, what if we just divide through by cos squared x, top and bottom? So then one of them's going to cancel out with the cos, and then I'm going to get x tan x, which is kind of looking a bit like that. And then when I divide by cos squared and I bring it inside the square, I basically just divide through by cos inside. So I'm going to get x sec x minus sine x. Not really what I want, but actually now I can see I just need to divide through by cos squared x again. Which is going to give x sec squared x tan x identical to the top over x. Remember, I'm just dividing by sec x inside the square. So sec squared x minus tan x. And it is almost identical to this integral. We just have a squared at the bottom. So it's going to be this exactly the same substitution. I'm going to get dx by du is 1 over 2 x sec squared x tan x. I will write it all out just to show it clearly. So times in by dx by du and integrating with respect to u. Which is going to give me a half of the integral, this time 1 over u squared, which I could write as a half integral u to the minus 2. So I'm going to get minus a half u to the minus 1 plus c minus a half times 1 over x sec squared x tan x plus c. You can leave it like this. Actually, you can just make it slightly nicer. If we times back through by cos squared, then we get minus a half cos squared x over x. Wait, I think sorry, that was a minus, wasn't it? I didn't see it. X minus, and then with my tan x sine over cos, I'm going to get sine x cos x, which looks a little bit like what we had at the start. Not actually, not really, but either of those absolutely fine. And yeah, those are 4 very enjoyable integrals.